right, so welcome today. We're going to be talking more about op amps. So before I go on with op amps, any questions from last time as far as op amps go? Yes.
So the triangle dude in the middle, is it just representing like an abstract thing? Or is it like, I don't know, so like, you know, is there like a specific thing that we could say it does? Or does what it does depend on what is around it?
So it depends on the configuration. So if you remember from when we did before, so this is inside what is going on with the op amp. So there's
That triangle has this dude going on.
correct. All of this circuitry is inside the op amp.
And every op amp has this exact same configuration on the inside. Like the triangle has the exact same thing on the inside.
It has similar circuitry inside of it.
Okay.
So some of them are different. This is all called the bipolar transistors. So this is a technology that uses just specific materials for bipolar transistors. There's other technology called CMOS, which has different materials. And so some circuitry is all CMOS based. So some of the chips you'll get will have CMOS, some will have BJTs, and then some have a combination of both called bi-CMOS. So the way they're made might be slightly different, but what they achieve and what you guys need to understand is more like, how do I use this in a circuit? So looking at that, kind of a generic thing you can think about is like, okay, I've got some black box. I typically, well, there was the 3 configurations that had only one input. Then depending on how that was kind of configured, whether it was a non-inverting amp or an inverting amp, it gave you a gain to it. So say it has a gain of 10. Then all of that the box does is amplify your input to give you an output that is 10 times the input. So this is basically, in generic form, what an amplifier does. So all of them are going to do something like this. So sometimes it might be negative. So it might be negative 10, might be a negative 11, you know, kind of around that range of a gain. And all it's doing is taking your input and multiplying it by some gain to give you an output. Does that help to kind of wrap your head around more of what the amplifier does?
Yeah.
Okay. Any other questions about that or more clarification? Okay, so this kind of an amplifier is going to be one of these configurations. So you have the non-inverting, the inverting. So the non-inverting gives you that 10, where it's going to be plus 10. Inverting would be a minus 10. And then you have the other configurations where you have multiple inputs, which are going to be the inverting and the subtraction difference, and the non-inverting summer. So those 3 would be more than one input. And with those, similarly, they're going to have some multiplication times an input portion, and then it's going to either add the 2 signals together with that amplification between them, or it's going to subtract off those. Then the last one, which we'll talk a little bit more about today, is this voltage follower, and when you would want to use like a voltage follower. Other term for that is a buffer, and we're going to go into a little bit more detail with that one. That one also has just one input, but it has no gain. So we're going to talk about like, why would you want to use that one? Okay, any other questions? Okay, so last time our goal was to being able to first look at an amplifier, which is the triangular symbol, and identify, is it a switch or does it have feedback? So that was the first goal. So if you remember that. Then the next one, if it was feedback, then it was to identifying what kind of feedback do we have. So today we're going to talk the next level, which is, well, once we know what kind of an amplifier we have as far as switch or feedback, and then if it is feedback, can we start to design these, and how do we design for these? When do we want to use a voltage buffer? And then we're going to talk about, the new one we're going to talk about is an instrumentation amplifier, which is going to be common to you guys. Okay, so these are kind of the symbols or circuitry that you're going to see. The non-inverting, inverting, how do you identify what configuration it is? Actually, let's go back. How do you identify if it's a switch or has feedback? Anybody want to say? Anybody remember? Yes, thanks.
If there's a path from the output to one of the inputs, then it's feedback.
Okay, no path from output to input, and then a feedback is path from output to input. Correct. Oh, it's really small. Okay. What identified if it was inverting?
If the input was going into the positive or negative.
Correct. So inverting would be input into which side?
Negative.
Correct. The negative side. And non-inverting is the opposite, right? Plus side. Okay, for the voltage follower, anybody remember what the difference was for that one? This one is easier to see visually. Kind of cut off that one, but so these are the differences. This is the voltage follower or buffer, and the one below it is which one? Correct, non-inverting. And so the difference between this is that this pathway goes directly from the output right back to the input, and there's also no pathway to ground from there. Here, there is a pathway back, but then there's also a pathway to ground. That's the difference. So this one has a path to ground, and this one has no path to ground. Does that make sense with pathway to ground?
Could that have a resistance or for the follower? Could that?
Yep.
Okay.
So you could have a resistor in there. There's still not a pathway to ground until you actually physically connect a resistor. As you can see, that R2 resistor is a connection right to ground from that input. So yes, I could have a resistor in the voltage follower and it would still just be a voltage follower. Any other questions or comments? Okay, so that's the difference between the voltage follower. How do you identify if it's inverting, summing, difference, or non-inverting? So first easy one is it has more than one input, okay? So if it has more than one input, it's most likely gonna be one of those three. So more than one input. Inverting summer. Where do you think the inputs are coming into? Correct. So inputs are into the negative side. And then for non-inverting summer, it's going to be the inputs into the positive side. And then with difference amplifier, you have a signal on both sides. One on the input, on the positive side, and one on the negative side. So they're on both sides. Does that make sense? So, looking at these, trying to hide that. This one is what? Get out of the way of the picture. Which one? Correct. Inverting summer. Correct. Oh, no worries. Yes, inverting summer. What about this one? Difference, correct, because you have one input V1 going into the negative and V2 goes into that positive side. Stand right here and then you can't see it. Okay. What's this one? I can't. I'll totally hide it. Okay. I am in the way, and this is opposite that. Okay, so this one is correct. Non-inverting summer because the signals are coming into that positive side. Okay. All right, good. All right, so I talked about generically where an amplifier or what an amplifier is. I gave you guys some examples last time. I want you guys to kind of think about what would be an application that you know of or have heard of that would be an amplifier would be used there. Okay. So maybe some musicians in here. So there's a guitar pedal that it actually can amplify and distort your signal and make different sounds from that, which is pretty cool. Sensors are a great one where you usually have, for sensors, it's going to be some small little voltage or current that comes out of it, and so you want to amplify that so that it is easier to determine what that value means. Radar would be another one where it usually is a low signal, and then you want to make sure it's a lot larger signal. Power would be another one. Speakers. So you kind of have to amplify it before you get to the end of the speaker, but so usually they're separate circuitry, but sometimes they'll be like noise canceling headphones will have some of the amplification going on in the headphone set itself. And so that needs to have some amplification, especially from the signal if it's a low input signal with low power. So great ideas. And yes, these are all applications. There was the Robo-B that we saw before. There was lots of amplifications needed to be happening with that one. So great ideas. Okay, so first off, what is this amplifier configuration? So identifying where the input signals are. This is tied to this one, and this is tied to this one. So remember when you see this news symbol that's just a wire sitting there with a voltage label on it, that means that it's the same as a voltage source itself connected to that same location. So this is what this means, is that V1 is actually a connection right next to the R1 that goes through a source to ground. And same thing with V2. So this is going to be, you're going to start to see this more commonly where it's just some wire with a dot and then a value labeled to it, like V1 or V2, where V1 or V2 would be your input sources. Okay, so those mean the same thing. All right, so this is a what type of amplifier? Thank you. Somebody said it, difference. Correct. So a difference amplifier, if I was to use superposition, I could actually get this answer without knowing, like remembering what the actual equation is. So we can use superposition here. If I do use superposition, I'm going to ground one or put 1 to 0, which means in this case it's going to go to ground because it's a voltage. So say I do this. What is my value if I have R3 going to ground, R4 going to ground? It's going to be 0 volts here, right? So one thing I like to look at when I think about op amps is that I get confused, and I used to get very confused about that symbol. It didn't mean anything to me. So what I like to do personally is to remove it. And what I'm going to replace it with is something I know. So removing it, and then I'm going to just put at the end a voltage source. So I like to put this little line through it, meaning like, okay, it's not a normal voltage source. It's kind of more of a different kind of source. So I usually just would draw it like this. So that's going to be some fixed voltage source there. And then because these are no longer having anything connected, it's easy to see that those currents are going to be 0. They're just some floating wire there. Now it hopefully is easier to see that this is going to be easier to solve. So solving this, I only have one branch, right? Through R1, R2 to V0. So the same current's going to flow through all of those. I can arbitrarily pick which direction. I'm just going to say arbitrarily it's going to go in this direction and this direction. Call it I. And then V1, remember, is a source itself going to ground. So as I do a loop, I have plus, minus, minus, minus. So plus V1, minus I R1, minus I R2, minus V out equals 0. And I can solve for V out here as V1 I'm wondering if it's easier to do I first. Let me go back and do I first. So solving this for I. If I take those over to the other side, this is just V1 minus V out, and then over R1 plus R2. So we have two unknowns here, right? So the trick with, like, how do we get the other equation for this one? So the other thing with an op-amp when you're solving it that you can do, which is due to the characteristic of it, and this is key on how to solve it, is that the V negative is equal to the V positive. And I forgot which one was which. So negative on the top. So this was Vn and this is Vp. So that gives us our second equation. So one equation and two equations, and now we can solve this. So knowing that Vn equals Vp, I also know that Vp is 0. You guys see that? So if this node is kind of 0 volts, then I can do a loop, because here's ground, and then at 0 volts here would be ground, and that would be one more loop. So plus V1 minus I R1 equals 0, and this gives me I is equal to V1 over R1. And that equals this. Or I can plug it into the first equation. And V1 minus V out over R1 plus R2 is equal to V1 over R1. I'm going to just kind of cross multiply these. So R1 plus R2, R1 for this whole thing gives me V1 R1 plus R2. And then I'm going to take that over to the left, so that becomes a negative, and plus R1 V1. And then bring the R1 V out over to this side. So R1 V1 minus R1 V1, they cancel out. So these are going to cancel. And I get that just V out is going to equal a minus R2 over R1 times V1. Does that make sense on the steps that I took here? Okay, so this is when I have a inverting amp. My plus side is grounded and my output is just this minus this resistor over this resistor. So this is just writing it out in that terms, RF over RS times my input. In this case, it was VS. So it's the same, and that's where that equation comes from. So if I identify like, oh, when I ground that, I have a inverting amp. then that would be the equation. What about, ground this one? When I ground this one, what do I have? So one question is, what's happening here? So I have to find the voltage at this node. And then this is what configuration? Which one?
Divider.
This is a divider, correct. So this is a voltage divider. So what is this value at Vx here? Anyone? How do you decide which resistor you want to find that value across? Yes.
Is it the one after?
It. Sorry, say that again.
Is it the one like after our reference?
Which one do you mean? R1 or R2?
R2.
Correct. So you're trying to find the voltage from ground to that node, which would be R2. So Vx would be V2 times R2 over R1 plus R2. And then you can either kind of lump all that up into like, okay, I only see Vx here. So Vx is my input in there. What configuration do I have now? Has one or more inputs, how many inputs does it have? It has 2 inputs from where? What is your input there? Vx and what else? It had 2, but I removed 1. So now it only has 1, correct?
Yeah.
So with 1 input, what kind of an amplifier configuration is this? Hint, it's going into,
Is it non-inverted?
so it's non-inverting, correct? So I could go through the same steps that I did before and take out the op amp, equate the Vn to Vp, and then do the one pathway to get that equation. In this case, instead of, back to this one, instead of 0 at Vn and Vp, Vn and Vp are going to equal Vx. So you have a slight difference there where your current, let's write it really quick. So your current I, so this node is going to be the same, Vx. So you have 0 minus IR1 minus Vx equals 0. So I is equal to a minus Vx over R1. So that will be the difference in equations. And then your end value, you can go back to the table that you have or derive it. But your equation is going to be this one. So R1 is this resistor here. and your output is equal to this, R1 plus R2 over R2 times Vs. So we can just use that, and that will be our non-inverting value. So R2 is this one, and this one was R1. So you just have to be careful that you're using the right variable value. Right. Over R1 divided by the one on the bottom, which is R1. That was confusing to use those. So input in this case is Vx, and this will be V out. And Vx then is here. So your total V out for this one is R1 plus R2 over R1 times R2 over R1 plus R2 times Vx, or times V2, sorry. So this ends up being, with these the same value, these cancel and I get R2 over R1, V2. So summing these together gives you R2 over R1 for V2, which is a plus, and then this one was a minus. So minus V1. So does that make sense how you can find an op amp if you can identify the configuration? Any questions on this? Okay. So much fun. Okay. So for a voltage divider, how do I want to say this? So very commonly, let me back up. So, you know, this is a way to have, okay, I have two different signals. Let me go back to the original one. So two different signals, let me write this, R2 over R1 times V2 minus V1. So V out is equal to R2 over R1, V2 minus V1. So it taking the difference and then it amplifies it based on the values of R2 and R1. So if R2 was 100K, R1 was 10K, this would amplify that difference by 10. Does that make sense? So that black, you know, that vague box, you have two inputs coming in. Draw it like this. So if R1 equals 10K, R2 equals 200K, or I'll do 100K, since I did that one already, 100K. This is gonna be 100K over 10K for a value of 10, and then amplifying the difference between the two. So this one would be a gain of 10, inputs are V1 and V2, and then our output is 10 times the difference between the two. And that's because of this configuration that we have it, the way it's connected up. So this sounds like a great way to be like, oh, well, say I have two strain gauges and I have, going back to that RoboB, say I have the RoboB and I've got two different strain gauges and I want to compare the two together to say what's my difference going to be. and then interpreting that to mean something like, oh, that means that this wing went down and this wing went up. So that turns into a small difference, turns into an actual physical difference of something happening. So this sounds like a great thing to do and use. Unfortunately, when you hook up any type of sensor, what happens is that you do something called a loading effect. And so most sensors end up having internally, you could model them with that Thevenin equivalence. So where we had that they have some type of internal resistance to them, and then they produce usually some type of voltage. So we call that output voltage from the sensor VTH. And then they have internally what's called a parasitic, a parasitic effect, that one on, where it creates, just based on the materials themselves, a resistance value. So not one that we designed, but something that is just present there due to the materials that are in there. So a parasitic effect. And so when we hook those up to something like that input that has that voltage division, instead of just the straight signal that comes in, we end up with that resistor, RTH, and VTH. So ideally we want this to be our input. So I'm going to call this instead a VY. So if this was my circuit, what is VY going to be here? So go ahead and write what you think VY would be here. Waiting for somebody to disagree with this. So, yes, those are all correct. And they're all the same, which is good. So, looking at this equation, Vy is VTH R2 over all of them. So is there any way that Vy can equal VTH here? So ideally you want to make sure that that signal that's coming from whatever device it is, the sensor, is actually what's going into the op amp. But because of all of these, remember this is a parasitic effect. And then these are values that, you know, are just there in the circuit. In order to make it have a difference, they have to be there. So ideally we want, going into that, VTH, but there's no way to make this equal to each other, right? Because these have to have some value to them. So R2 has to have some value, R1, R2, and RTH all have values to them. So it's going to be something less than VTH. So this is called a loading effect. Where you're calling it basically the value is not equal to what you want. So in this case, we want VTH, for example. So that is where the buffer comes in. So can use a buffer. I can't get another page. So with the buffer, bring it down here. Oh, where'd it go? Okay. So looking at this buffer, if we do what we did before, remove the buffer, and we have 0 going in here, 0 going in there, and we put a source here of value V out, then this node is going to equal what? So this was Vn and this is Vp. So I'll just say Vn equals V out. Hopefully you see that. So it's Vn equals V out. And then what I said, remember, was the key to solving the op-amp is to say Vn equals Vp. So in this case, if Vn equals Vp, that's also equal V out. And we also know that Vn or Vp is equal to Vn. So V out is going to equal Vn. So it's actually a pretty simple circuit, and all it's doing is it has no gain to it because the input is equal to the output. What it provides is a buffer so that the resistance doesn't affect that output. So what I mean is that even though I may put a resistor here, I'll just call it RL, this resistance doesn't change the value of V out for this at all, because this acts like a voltage source. So it is taking, internally, it takes current and pulls it to keep the current here equal to give you V out at that node, at this node. So this node is always going to stay equal to V out. So this is the way it can act as this buffer and keep that value at that node, V out node, V out. So if I put on, my VTH here, with that parasitic effect of resistance RTH, now there's nothing to divide down and become a voltage divider because that's a floating wire going into the op-amp. Do you guys see that too? So because there's no current going into that resistance, there's no voltage drop across this parasitic. And so my Vn is equal directly with my VTH, which equals my output, and I can keep it exactly at that same value. So one thing we can do is put these voltage followers as the inputs onto this differential amplifier. And now we know like the signal itself is not being what's called attenuated or reduced down from its original value. But this is kind of hard because to change the gain in here, I have to change two resistor values, R2 and R1, in order to change and have a gain difference. So what they created instead is called this instrumentation amplifier. And with this instrumentation amplifier, they use this resistance here, RG, and only one resistor to control the gain. So, find this. Let's see, it would be R3 over R2. Sorry. Okay. So you can drive this the same kind of way that we did before. Okay. Yeah. So it's R3 over R2 are going to be your main amplification there, but then you have this RG, and so you can tweak this between R1 and RG by just using the one resistor to give you a gain difference. So they actually have these kind of chips that already have all this configuration called an instrumentation amplifier chip. So you guys may want to use that as mechanical engineers if you are like, okay, I have a sensor, I'm going to use the chip that's already made for all of this. You just have to note that that RG is what's going to be controlling your gain up and down. Okay? So let's now look at, we have only talked about like fixed 5-volt values or some other voltage on there. What happens when we have an AC input into these op amps? Yes?
Sorry, could you just scroll a little bit? Or down, sorry. What is that sorry, what's that last term there? Can you say it?
So these are really poorly labeled. This is VN minus and this is VN plus. And so these are VN minus and VN plus. Try and write them better. VN plus side minus the VN minus. Hopefully that's easier to read. Okay, so nice that there's already a chip that has multiple op amps on it like this, and then it's designed to be like, oh, I only need to really tweak one resistance to change it or to change this gain instead of having the two. And usually it's like an external resistor that you put a potentiometer and then you change it until you get like a zero value of where you want to start with it. And then you can change it. Okay, so moving to AC. First off, what is the output of this first amplifier? One, what is it? So what kind of configuration is this? Great, inverting, correct. What is the second amplifier? So there's just one wire. So it's going into the inverting one, but it doesn't have a pathway from here to ground. And so it is that, what was the one that doesn't have a pathway to ground there?
Neither have a pathway to ground.
So, yeah, I see what you're saying. So this does have a pathway to ground, it's just through the input source. So this one has a pathway to ground. This one does not. So I know that looked confusing because it didn't have, because it kind of looks like an open, but because that's an actual source, it does have a pathway to ground, whereas this new pen is driving me nuts. This would be the buffer or voltage follower. So if this is inverting, if you want to go back and look at that equation, what is the gain for the inverting? Go grab this one. So what is your gain here? Okay, so negative 7/3 and 7/3, 7k over 3k. So these are all correct as far as if I asked for just the gain. The gain would actually be a negative because it's inverting. And so the negative 7/3 would be the correct one. So negative because it's inverting, so negative 7/3 or negative 2.3. So what is the output here for this V out? Correct, it's the same. And it will be the same as VA, which is VN. So negative 2.3 VN. And so this is negative 2.3 VN. So graphing this, it's over here. If my output is based on this input, then when I have an amplitude of 1, where am I on this graph? When I have a +1, my output's going to be negative 2.3, correct? I think I heard somebody say that. So when it's +1 here, it's going to go down to, I'll say this is negative 2.3, to this value here. And then it's going to be following as it goes down. And then when it's negative, it's going to go up by 2.3. So it's going to look like this. And so it will look similar to this. Okay, so this would be my V out. Does that make sense? So all it's doing is taking, even though it's an AC signal, if you look at the peaks, you know that it's going to be a sinusoid in between those peaks. And then when it's negative, it's actually output is going to be a plus. And when it's positive, the output's going to be the negative. So that's why it's called inverting. It's inverted the input signal. And for a non-inverting, it's going to follow when it's plus, it's still going to have an output that's plus. Okay. All right, so on this one, let's first find this value here. I'm going to call it Vx. So take some minutes to find Vx, and then once you feel comfortable with Vx, then find VO. So what's the first configuration? Correct. So it's gonna be inverting amplifier. And the second one is gonna be. Correct. So it's inverting and inverting. Uh-huh. So you could use just a non-inverting, so when you get to control systems, if you take your control system class, you learn that you actually have a frequency response, and you get two poles that have each amplifier. And that's gonna affect your overall control system. So that's, do you wanna use one? So that's where it fits to begin with. So it's more about controls and how many poles and zeros do you create. Not with an ideal. So with a non-ideal, there is a small current that actually goes into that first line. And so it would give you a small voltage node. And it's gonna offset the other side, so it tries to cancel out some of that non-ideal effect. But as far as like the ideal configuration is just to try to get an amplification that's effective. Just to get an easier connection.
Oh, okay. And also one other question.
So those all look like they agreed, except for I think there was a sign error on one of them. So first one is inverting. And you identify the key resistors to determine how much it's inverting, which are going to be these two. So Vx is going to be a negative 24 over 6 times Vn, so that's a negative negative 4 Vn. Is that correct? And then Vn is 0.1, so negative 0.4 volts. And then the second one is also inverting. And these two will be your key resistors. So then 100K over 20K, a negative of that. And so V out will equal negative 5 times negative 0.4 volts to give you a plus 2 volts. Sorry, there you go. So the 100 over 20K, and then that is 5, so you have a negative 5 times the negative 0.4 volts to V2 volts. So what's going on with this right here? That 10K. Any thoughts? What's that? That doesn't change any of the output, right? So it's really not doing anything to this circuit. So you can pretty much ignore it. What if I put a resistor right here, or an RL resistor? If this is 100K, does that change my output VO? It doesn't change the output VO at all, correct? So RL does not change your output VO. So those are some key understanding of the characteristics of the op-amp, is that it acts like that voltage source. So when I put a resistor on there, it doesn't do anything. It will change the current going to it based on that output VO, because if it's 100K, how much power is going here? Or first off, what will be IL? It will be V naught over RL, correct? And that's 2 in this case, so we have 2 over 100K. So what if RL is instead 1K? IL will be 2 over 1K, right? So it's going to be a lot larger. So all that's doing is changing that current, and that voltage stays fixed. So depending on what load I have, how much power I need to it, I can determine how much resistance I need to go out. All right, any questions about this? You guys feeling more comfortable with op amps? Okay, so next week I'm actually out of town, so there will be in-person lecturing. There's 2 sections of your course, so the instructor of the other section is going to be coming and teaching here. So she'll be talking about capacitors for Tuesday and then inductors on Thursday. Tonight you'll have due the Unit 1 feedback, so it's feedback about the exam and anything from Unit 1, so that's due by tonight. And then next Thursday will be your first homework on this section, and then your next quiz will be next Friday. So no quiz this Friday or tomorrow. So, all right, see you guys.